हेलो। हाँ बताओ।
Good evening, everyone. So, in the last session, we discussed about the energy of electron in a hydrogen atom, right? We also calculated about the radius of electron in different orbits, right? Radius of orbits, right? Uh, and also we calculated the velocity of electron in different orbits, right? We calculated the total energy, and we also studied that the transition of the electron from whenever transition is there for the electron from higher energy level to the lower energy level, right? So radiation is emitted, right, in the form of photon, and that radiation, those radiations are of different wavelengths depending upon the energy difference between the two energy levels between which the transition is taking place, right? So today we'll be discussing the hydrogen spectrum, right? There will be a band of wavelengths emitted, right? Depending upon the transition, right? So that's that band of wavelengths we call as spectrum, right? And we'll be studying this spectrum for the hydrogen. That's why we call it a spectral series of a hydrogen atom, right? So the total energy, we know that transition takes place between higher energy level to the lower energy level, right? So let's suppose this is the higher energy level E2, right? And this is the lower energy level E1. Let's suppose the n value for this energy level is N2 and the n value for this energy level is N1, right? Now, electron is initially present in the higher energy level, right? In the higher energy level, right? Now, this electron will make a transition, right? Transition to lower energy level, right? And corresponding to this transition, it will emit a radiation, right? And let's suppose this radiation will have a wavelength of lambda, right? So corresponding to this transition, the radiation will be emitted of wavelength lambda, right? Now, the energy of this photon will be equal to the energy gap or the energy difference between two energy levels, right? And we know that the total energy of electron in any orbit is given by its minus me to the power 4 upon 8 epsilon naught square, right? N square h square, right? So this was the energy, right? This was the energy. This was the energy of electron in any orbit, right? Similarly, if we calculate the energy of this or electron in this orbit E2, let's suppose that will be E2, that's equal to me4 minus me4 8 epsilon naught square, right? N2 square h square, right? N2 square h square. And similarly, energy of this final energy of this electron in this lower energy orbit will be E1, right? Once the transition is made, right, it will be minus me to the power 4, right, upon 8 epsilon naught square, N1 square h square, right? So this will be the final energy of electron. Now the energy of this photon will be equal to the energy difference between the two energy levels, right? So energy of this photon, let's suppose energy of this photon, we know that that is equal to h nu, right? Or we can write that as hc upon lambda, right? Hc upon lambda. So energy of this photon will be, let's suppose E is the energy of photon, right? Ep is the energy of photon. That will be equal to the band gap or energy gap between the two energy levels, right? That's E2 minus E1, right? E2 minus E1. So E2 is minus me to the power 4, right? Upon 8 epsilon naught square, right? N square, N2 square, H square, right? Minus E1, or it will be plus me4 upon 8 epsilon naught square, N1 square, H square, right? So this will be the energy difference between them. So we'll be taking me to the power 4, right, upon 8 epsilon naught square, h square as common, right? This will be a common term here, and we'll be left with 1 upon n1 square minus 1 upon n2 square here, right? So this will be the energy difference, right? And this energy difference will be equal to the energy of photon, that's equal to hc upon lambda, right? Hc upon lambda, right? Hc upon lambda. That will be equal to me to the power 4 upon 8 epsilon naught square, right? H square. And in the bracket, we'll have 1 upon n1 square minus 1 upon n2 square, right? So the value of lambda from here comes out to be equal to me to the power 4, right? That's equal to 8 epsilon naught. It will be 1 upon lambda, right? 1 upon lambda. So 1 upon lambda will be equal to me4 upon 8 epsilon naught square, right? It will be h cube multiplied by c, right? Where c is the speed of light. It's 1 upon n1 square minus 1 upon n2 square, right? So this will be the 1 upon lambda, right? That's what we call as 1 upon lambda. We call it as wave number, right? We call it as wave number. So me to the power 4, 8 epsilon naught square h cube c, and 1 upon n1 square minus 1 upon n2 square. Now this we can see here this value m, e, epsilon naught, h, and c, these are all the constant values, right? So we can write this constant value as me4 8 epsilon naught square h cube c, right? And this is a constant, and this constant we call as a Rydberg's constant, right? We call it as Rydberg's constant. Rydberg's constant, and its value is approximately equal to 1.1 into 10 to the power 7 meter inverse, right? So this is the value of this Rydberg's constant. It means that we can write, in short, we can write the value of lambda, 1 upon lambda, as value of 1 upon lambda will be equal to, that will be 1 upon lambda, that will be equal to r times, where r is a Rydberg's constant, right? Multiplied by the factor 1 upon n1 square minus 1 upon n2 square, right? N2 square, right? So this is the value of the 1 upon lambda. From here, we can calculate the wavelength of the emitted photon, which makes a transition from higher energy level to the lower energy level, right? So this photon makes a transition from higher energy level to lower energy level, whose wavelength is calculated in from this equation, right? So similarly, the transition, many transitions are possible, right? Electron can make transition from any higher energy level to lower energy level, and corresponding to that transition, right? Corresponding to that transition, there will be a spectral line, right? There will be a spectral line. So this is the energy of each. You can see in this bracket here, or in this table here, you can see we have the energies of different energy levels. For n1, we have minus 13.6 electron volt. For n equal to 2, we have minus 3.4 electron volt. For n equal to 3, we have minus 1.5 electron volt. And similarly, for n equal to infinity, the energy of the electron is 0. And the positive of all this energy will be called as the binding energy. It means that if we give this much of energy to the electron, then electron will absorb that energy and will go to the infinity, or will be unbounded from the atom, right? It will be unbounded from the atom. So the energy of the level least energy state, right? The energy of the least energy state we call as ground state, right? We call it as ground state, right? So n equal to 1 here is a ground state, right? We call this as ground state. G is ground state. And n equal to 2, it's the second energy state. We call it as first excited state, right? We call it as first excited state. First excited state. And similarly, n equal to 3 will be a second excited state, right? It will be called as second excited state, right? So n equal to 1 is called as, for hydrogen atom, n equal to 1 is the ground state. It's the state of least or minimum energy, right? Ground state is the state of minimum energy, right? So n equal to 2 is the first excited state for here, for the electron here in the hydrogen atom. For n equal to 3, we call it a second excited state. Similarly, n equal to 4 will be third excited state. N equal to 5 will be fourth excited state, right? Now, an electron can make transition. Let's suppose the electron is electron is present in n equal to 5, right? Electron is present in n equal to 5, right? It can make transition from n equal to 5 to n equal to 3, right? It can make transition from n equal to 5 to n equal to 4. It can then make transition from n4 to n2, or it can make transition from n4 to n3, right? So electron can also make transition from then n2 to N1, right? So there are many band of spectral lines, many spectral lines possible, right? For the transitions, right? So that the electron reach the ground state, right? So electron can make many transitions, right? Corresponding to each transition, there will be a photon emitted, right? Equal to the energy gap, right? Equal to the energy gap. So these photons or these radiations actually correspond to the spectral lines, right? And each each radiation is having a unique wavelength or unique frequency, right? Because of the unique energy gap, right? And we can also see the energy gap between the two consecutive as we move higher, as the value of n increases, the energy gap between the two consecutive energy levels actually decreases, right? It decreases continuously, right? So corresponding to each and every transition, there will be a radiation emitted, right? And if the electron makes a transition from a lower energy state to higher energy state, then the electron will absorb the energy equal to the energy gap between the two states, right? To make a transition. Now, mm, now electron can make a transition from any higher excited state to lower excited state. We know that corresponding to every transition, the wavelength emitted will be given as by this equation, that will be R times 1 upon n1 square, right? 1 upon n2 square, right? 1 upon n2 square. So 1 upon n1 square, 1 upon n2 square, right? Now, let's suppose our electron makes a transition, and our electron makes a transition from any higher excited state to n equal to 1, right? N1 equal to 1, right? For from any higher excited state to n1 equal to 1, it means that if the state final state of the electron is n1, that's equal to 1, then such transition or such band of spectral lines emitted for the transition from any higher energy state to n equal to 1, this series of spectral lines we call as Lyman series, right? We call it as Lyman series, right? N2 can have any value, right? N2 can have any value that will be equal to n, right? So this series we call as Lyman series for n1 equal to 1. So 1 upon lambda will be equal to 1 minus 1 upon n square, right? Right? So let's suppose an electron makes a transition from n2 equal to 2, right? N2 equal to 2, right? So the energy or the wavelength can be calculated as, that will be 1 upon lambda, that will be equal to 1 upon 1 minus 1 upon n square, that will be 2 square, right? It will be equal to 3 r upon 4, right? So this will be the 1 upon lambda, right? From here, lambda will be equal to, so this will be 1 upon lambda will be equal to r times, right? It will be r times 1 minus 1 upon 4, right? So 1 upon lambda is equal to 3 upon 4, 3r upon 4. So lambda will be 4 upon 3r, right? So this is the value of the lambda, right? So this is the wavelength, right? This is the wavelength of the emitted radiation, right? So similarly, any transition can be made for this Lyman series. So there are actually infinite number of transitions possible for n2, right? If the n1 value has the fixed value that's equal to 1, then we call as this transition we call as Lyman series, right? And this series actually falls in the UV region, right? This falls in a UV region, right? This series actually falls in a UV region, right? Of the spectrum. This Lyman series actually falls in a UV region of electromagnetic spectrum, right? This falls in a UV region of electromagnetic spectrum. Similarly, let's suppose that if we have n1 value as equal to n1 value equal to 2, right? Such series we call as Palmer's. called as Balmer series, right? So for Balmer series, N1 is equal to 2, or we can say 1 upon lambda for Balmer series will be equal to R times, right? 1 minus, it will be N1 is 2, that will be 1 upon 4 minus 1 upon N square, right? 1 upon N square, right? For Balmer series, if N is equal to 3, right? N equal to 3, it means the transition is from N3 equal to N2, N equal to 3 to N equal to 2. And this line we call as H alpha line or first Balmer line, right? This we call as H alpha line or first Balmer line. Similarly, for N equal to 4, right? N equal to 4, if the transition is from N equal to 4 to N equal to 2, we call it as H beta line, right? This is H beta line. Call it as H beta line, right? For the Balmer series. So this we'll call as the Balmer series, right? So for Balmer series, N1 value or the final transition state will be equal to 2, right? Similarly, we have other series as well, right? We have Paschen series, right? For Paschen series, we have N1 value equal to 3, right? So 1 upon lambda will be equal to R times, it will be R times 1 upon 3 square, that will be 9 minus 1 upon N square, right? So this will be a Paschen series, right? And the fourth one will be bracket series, right? Bracket series. And for bracket series, we have N1 value equal to 4, and the value of wavelength will be 1 upon lambda, that will be equal to R times 1 upon 16 minus 1 upon N square, right? Where N is the higher excited state, right? It's the higher excited state. And we can also have Paschen series, bracket series, and Fund series, right? For this series, we have N1 value equal to 5, right? And 1 upon lambda will be equal to R times 1 upon 25, right? Minus 1 upon N square. So this is how we can actually calculate the wavelengths of the different series, right? So it makes us, these are the spectral series, right? Different spectral series of hydrogen atom. We have Lyman series, we have Palmer series, right? We have, so each and every series is having a band of wavelengths or the band of the frequencies, right? They fall in different regions. Like we have this Lyman series falling in the UV region, then we have a series falling in the visible region, right? We have the series falling in the IR region, right? So all these series, Lyman series or the spectral series falls in the different regions of the electromagnetic spectrum, right? So this is what we call as the spectral series of hydrogen atom, right? Now you can see here the conclusion is here, right? Let's suppose that there is a Lyman series, right? A Lyman series. Let's suppose this is the ground state. This is the ground state. This is the first excited state, second excited state, third, fourth, and fifth, right? Now, an electron can make a transition from N5 to N4, right? It can make N4 to N5 to N1, N4 to N1, right? N3 to N1, right? This series of line will be actually a Lyman series. Then we will have Balmer series. This is the Balmer series. Then we can have, right? We can have Austen series, right? We can have bracket series and we can have full series as well. So these are all the different series of the spectral lines, right? Depending upon the transition from the higher energy state to the lower energy state, right? Now, let's try to solve this question, right? Let's try to solve this question. A hydrogen atom in the ground state is excited by radiation, right? Is excited by radiations of wavelength 975 angstrom. Find the energy state to which the atom is excited, right? How many lines will be possible in emission spectrum? So we have to find a hydrogen atom that is excited by radiation of wavelength 975 angstrom, right? So it means that this electron has actually uh, absorbed some energy, right, from the external radiation, and it goes to some higher some higher excited state, right? Now, if this electron makes a transition, right? If this electron makes a transition, it will actually emit this energy equal to the same wavelength, right? That's 975 angstrom, right? Or we can say that the wavelength, once the electron makes a transition from this higher energy state, it will emit a radiation equal to the same wavelength, that's 975 angstrom, and that will be equal to R times 1 upon n1 square minus 1 upon n2 square, right? Minus 1 upon n2 square, correct? So it means that the value of lambda is given as 975 angstrom, right? 975 angstrom, we can write it as 10 to the power minus 10, and the value of R is 1.1 into 10 to the power 7 meter inverse, right? uh, 7 meter inverse. From here, the value of n1 is because it's a transition to the ground state, right? The ground state value is 1, and to the higher energy state, the value of n will be n. We have to calculate this value of n. So from here, we can actually calculate the number of, or we can calculate the higher energy state to which the electron has actually jumped, right? So from that, once the electron jumps, right? Once the electron jumps from the higher energy state, let's suppose electron jumps to n equal to 3, right? N equal to 3 or n equal to 4. Let's suppose electron jumps to n equal to 4, right? This is 1, this is 2, this is 3, right? This is n equal to 4. Now the electron can emit different types of spectral lines. The electron can make a direct transition from n equal to 4 to n equal to 1. It means that it will emit a Lyman series, right? Or the electron can emit a Balmer series, right? Or the electron can emit a Bastian series, right? So these are the types of transition possible, right? Between n equal to 4 and n equal to 1, right? Or or the electron can make a transition from this excited state n equal to 2 to direct n equal to 1, right? After making a transition from n equal to 4 to n equal to 2, the electron will make a transition from n equal to 2 to n equal to 1. Now, so from here we can see there are four transitions possible, right? Four transition possible. Let's see. The number of transition will be number of transitions, or number of spectral lines, right? Will be given as n into n minus 1 upon 2, right? Upon 2. The value of n here is 4, right? It will be 4 minus 1 upon 2, right? So it will be equal to 6, right? It will be 6 lines. So it means it has to emit us 6 lines, right? So it means that two more, we have made that 4 lines here, right? The electron made a transition to this energy state, right? Now the electron once it makes a transition from this state to this state, it can make a transition from this state to this state then, right? Right? Or the electron can make a transition from this state to this state directly, right? So these are the 6 transition lines possible, right? This 6 line transition possible for the electron, right? Electron can jump from n equal to 4 to n equal to 1, or the electron can jump from n equal to 4 to n equal to 2, then n2 to n1, right? Similarly, it can jump from n4 to n3, n3 to n2, n2 to n1, right? So in this way, 6 lines are actually possible, right, for different spectral series, right? So the number of spectral lines, or the number of lines emitted, possible lines, right? It's not like that electron will emit all these transitions. So these are the number of possible lines, right, that the electron can emit. That's n equal to n minus 1 upon 2, right? So these will be the number of lines emitted, right? Now the question is that find the atomic number of atom when given that its ionization potential is equal to 122.4 volt, right? So the ionization potential of electron is given as 122.4 electron volt. We know that ionization potential is actually, we know energy of electron is given as minus 13.6, right? 13.6 into z square upon n square, right? Or the ionization energy has to be equal to plus 13.6 into z square upon n square, right? It will be the ionization energy for the electron, right? For the hydrogen atom, right? So it's given that the ionization energy is given here. It's equal to 122.4, right? Let's suppose we're finding this ionization energy from the ground state. So the n value will be equal to 1, right? N value will be equal to 1, right? So the ionization energy will be directly 13.6 multiplied by z square, right? Multiplied by z square. Now it's given equal to 122.4. So we'll substitute the value of ionization energy 122.4, right? That will be equal to 13.6 multiplied by z square. Or from here, 122.4 upon 13.6 under root, we'll take the root of this, we'll get the value of z, right? We'll get the value of z. So z, this will be the atomic number, right? This will be the atomic number. So approximately, it will be around, it should be around 3, right? Atomic number for this atom should be equal to 3, right? Now, the question is that we have to find the maximum wavelength of bracket series of hydrogen atom, right? Bracket series of hydrogen atom, right? For the bracket series, we have Lyman series, Balmer series, Bastian, and bracket. So for bracket series, we have N2 value equal to 4, right? N2 value equal to 4. So the maximum wavelength will be emitted when the electron makes a transition like from n equal to n to equal to infinite, right, to the n equal to 1, then the energy gap will be maximum, right? For the from n equal to infinity to n2 equal to 4, right? uh, n2 equal to infinity to n equal to n1 equal to 4, right? So n2 is equal to infinity, n1 is equal to 4 for the bracket series, or that will be the maximum, that will be for maximum energy, right? If this is the maximum energy, then it will be the emission of least wavelength, right? The wavelength will be minimum. So this will be for maximum energy, right? Maximum energy or least wavelength. Maximum energy or least wavelength. But we have to find the wavelength transition. We have to find the transition for the maximum wavelength. So for the transition to be of maximum wavelength, it should be the transition between the two energy levels where the energy gap is minimum, right? Where the energy gap is minimum. So for bracket series, energy gap will be minimum for n1 equal to 4, right? And n2 equal to, right, n2 equal to 5, right, n2 equal to 5. So this will be the minimum energy gap, and the wavelength will be maximum. So 1 upon lambda will be equal to then r times 1 upon n1 square. It will be 1 upon 16 minus 1 upon 25, right? So from here you can calculate the wavelength of the what we call as maximum wavelength of the bracket series, right, of hydrogen atom, right? So this will be the maximum wavelength of bracket series of hydrogen atom. Now coming to the last question of this hydrogen spectrum, right? For the given transition of electron, obtain the relation between lambda 1, lambda 2, and lambda 3. Now you can see here the electron makes a transition, and electron is making a transition, right? An electron is making a transition from it's making a transition from E3 to E1, or it can make a transition from E3 to E2, then E2 to E1. But the total energy has to be conserved, right? That is E3 should be equal to E2 plus E1, right? We can write E3 as Hc upon lambda 3, right? It will be Hc upon lambda 3, right? E2 will be Hc upon lambda 2, right? And E1 will be equal to Hc upon lambda 1, right? Hc upon lambda 1. From here, Hc and Hc will get cancelled. We'll get the value lambda 3 equal to, that will be equal to lambda 1 multiplied by lambda 2, right, upon lambda 1 plus lambda 2. So this will be the value of wavelength lambda 3, right? So that's it with respect to the atom or the hydrogen atom. We're done with the hydrogen atom. We'll be starting or moving towards the nucleus, right? We know according to the Rutherford's model, uh, we discovered the center of the atom, that was called as the nucleus, right? Central core of every atom is called as nucleus, and it was discovered by the Rutherford during the alpha particle scattering experiment, right? And the radius of this nucleus, or the nuclear size, what we call it, is of the order of femtometers, right? Of the order of femtometers, or we can say it's of the order of 10 to the power minus 15 meters. That's 1 femtometer. And while the size of the atom is of the order of angstrom, that's 10 to the power minus 10 meter, right? And nucleus, we know nucleus contains two subatomic particles. One is proton, another is neutron, right? And together we call them as nucleons, right? Nucleons. And the any nucleus is actually represented by right, by mass number A, right, and the atomic number Z, right? Mass number A and atomic number Z, where A is the number of sum of protons plus the neutrons, that's the mass number, and Z is the number of protons present in the nucleus, that's the atomic number, right? So any nuclide will be represented by this, right? Now talking about the types of the nucleus, we can have many types of the nucleus. One of the type of nucleus is what we call as isotope. So isotope are those atoms, right, or those elements which are having the same number of protons in the nucleus, and it can have different mass number, but the number of protons will be same, right? But the mass number will be different. One of the famous example is of chlorine, right? Chlorine. You can see chlorine has two isotopes. One is chlorine 35 and chlorine 37. You can see both chlorine is having the same number of protons in their nucleus, 17 each, right? 17 each, but their mass number is different because their number of neutrons in the nucleus is different, right? So for this chlorine atom, the neutron numbers are 17, right? Neutron numbers are 17, but here the neutron numbers are actually equal to number of neutrons will be here equal to 18, right? It will be equal to 18. So number of neutrons here will be equal to 18. Now here the number of neutrons are actually not 18, right? It will be 20. So the number of neutrons here is 20 and number of neutrons here are 18, but they are having the same atomic number z equal to 17, right? Z equal to 17. That's the number of protons, right? So they are having the protons equal to 17 each, but the neutrons are 20 in 30 Cl37 and 18 in Cl35. Then we have another type of nucleus, what we call as isobar. So isobars are the atoms or the nucleus having the same number of same mass number, right? Same mass number, right? They can have a different atomic number, but same mass number. Suppose we have the isotope of the nitrogen, that is N14, and isotope of carbon, that's C14, right? So carbon has the atomic number of 6 and nitrogen has the atomic number of 7, right? They are having different atomic numbers, but they are having same mass numbers, right? It means that the number of mass, the number of neutrons in carbon 14 are more as compared to the number of neutrons in nitrogen, right? So here the number of neutrons is actually 8, right? And the number of neutrons here are 7 only, right? 7 only. So they will have same mass number but different atomic numbers, right? Such nucleuses we call as isobars, right? And then we have isotones, right? Isotones are the atoms of the nucleus which are having the same neutron numbers, right? They are having the same neutron numbers, or we can say they have the same A minus Z values, right? So the number of neutrons present in the lithium are actually 7 minus 3, right? 7 minus 3, that's equal to 4, and beryllium 8 is also having the number of neutrons equal to 8 minus 4, that's equal to 4, right? So they are having the same number of neutrons, that's why we call them as isotones. So we have three types of nucleus, right? We can have more types of nucleus as well, but this is sufficient for you: isotope, isobar, and isotope. Now let's talk about the size of nucleus, right? We know that the size of nucleus is generally of the order of femtometers, right? But what is the actual size of nucleus, right? It depends upon the mass number as well. So as the number of neutrons or number of nucleons increase in the nucleus, definitely the size of the nucleus will change, or the size of nucleus will increase, right? Now this radius of the nucleus is actually directly proportional to the a to the power 1 by 3, right? A to the power 1 by 3, or where a is nothing, it's the mass number, right? It's the mass number, right? So radius of a nucleus is proportional to a to the power 1 by 3, where a is the mass number, right? So where we can replace this proportionality with r naught, right? A to the power 1 by 3, right? Where r naught has the dimensions of the length, and it's equal to 1.2 femtometer, right? Or we can say it has the value 1.2 into 10 to the power minus 15 meters, right? So this is how we can calculate the radius of a nucleus, or size of a nucleus, right? So size of a nucleus is actually proportional to the a to the power 1 by 3. Now talking about the volume of nucleus, right? Volume of nucleus. So volume of nucleus will be actually, let's suppose it will be proportional to r cube, right? Volume will be proportional to r cube, right? And we know r is proportional to a to the power 1 by 3, or we can say volume will be proportional to the a, right? So for nucleus, the volume of a nucleus will be directly proportional to the mass number, right? A. So volume will be proportional to the mass number A. Now the radius will only depend upon the mass number, volume will also depend upon the mass number. Now talking about the density of nucleus, right? Now talking about the density of nucleus. So density is nothing. Density is what we call as for any object as the mass per unit volume, right? Mass per unit volume. It's the mass per unit volume, right? That's the density. Now let's talk about the density of this nucleus, right? We know that if A is the mass number, right? If A is the mass number, right? If A is the mass number, if A is the mass number of a nucleus, right? If A is a mass number of a nucleus, right? If A is the mass number of a nucleus, then the A are the number of nucleons present in the nucleus, or A is the mass number of a nucleus, right? So let's suppose approximating it, let's suppose MP is the mass of proton, right? Mass of proton, and A is the mass number, right? A is the mass number. Now, this will give us the total mass of nucleus, right? Depending divided by the volume nucleus, that's 4 by 3 pi r cube. It will be r naught cube, right? Into A, right? From here, A and A will get cancelled, right? We'll get the density value as MP, right? MP upon 4 by 3 pi r cube, right? Pi r cube. And we know that mass of proton is equal to the it has the mass equal to one atomic unit, right? One atomic unit, right? uh, One atomic unit. And we know that one atomic unit is actually the mass of a mass of an atom, right? Mass of a one atomic unit is equal to 1/12 of the mass of a carbon atom, right? If we have a carbon 12 isotope, right, then the 1/12 of the mass of the carbon 12 isotope will be called as one atomic mass unit. And the mass of proton is actually equal to 1.0027 atomic mass units, right? So this is the mass of uh, proton, right? This is the mass of proton. So if we substitute the value of mass of proton here in this equation, we'll get the value of density here equal to 2.3 into 10 to the power 17 kg meter per cube, right? This will be the density of a nucleus, right? So the density of nucleus is actually very huge, and it's a constant for all nucleuses, right? That's what we call as 2.3 into 10 to the power 17 kg per meter cube, the density of nucleus, and it is independent of the mass of nucleus or the mass number of nucleus. We can see here it was independent of the mass number of nucleus, or it's constant for all nuclei, right? Now let's see what are the different types of forces inside the nucleus, right? There are three types of interactions or forces between nucleons, right? These interaction, one is the gravitational force, right? And we know that the gravitational force is the weakest force in the nature, right? It's the weakest force in nature, right? So it means that for in case of nucleons, the gravitational force will not have any impact at all because of its weak nature, right? It is the weakest force of all. And the second interaction is the electrostatic repulsion, because we have proton and proton, they are both positively charged, so there will be electrostatic force of repulsion, or there will be a Coulombian force in between them. And it is only applicable for the protons because neutron itself is a neutral particle, right? And electrostatic force of attraction is much stronger than the gravitational force, right? Then we have the strongest force of the nature. That's what we call as nuclear force. And this strongest interaction between the nucleons actually holds nucleons together to form the nucleus. And it is powerful enough, right? It's powerful enough to overcome the all the electrostatic repulsions, or we can say electric repulsions between proton and proton, right? So that's the power of nuclear force, right? So we have three forces there. One is the gravitational force, another is the electrostatic force, and the third one is the nuclear force. And nuclear force overcomes all these forces, right? Electrostatic repulsions to overcome and holds the nucleons together, right, to form the nucleus, right? So these are the different forces inside the nucleus. Now, nuclear force is a very important force, right? It's the strongest force in the nature, and it's only working between the nucleons, right, inside the nucleus. And another important property of this nuclear force is that it's a very short range force, and it is applicable only up to a distance of 3 to 4 uh, 3 to 4 what we call 3 to 4 femtometer, right? more than this distance, nuclear force becomes almost zero, right? Almost zero. It becomes negligible, right? So it very much depends upon distance, right? So for a particular distance, for a particular range of distance up to 0.8 femtometer or above, right? This nuclear force is actually attractive in nature, right? And once the distance is less than the zero point 0.8 femtometer, it decreases further, then the nuclear force becomes repulsive in nature, right? So nature of the nuclear force is both attractive as well as repulsive, depending upon the distance between the nucleon, right? If the distance is greater than the what we call as 0 0.8 femtometer, then it will be attractive in nature, and if the distance decreases less than 0 0.8 femtometer, it will be repulsive in nature, right? So small variation in distance may cause a large change in nuclear force, while electrostatic force remains almost unaffected, right? So electrostatic force depends upon the distance, but there is a very small variation in the distance. So electrostatic force actually does not vary, right? Now, fifth important property about the nuclear force is that it is charge independent. So it interacts between the neutron and neutron, as well as proton and proton and neutron as well. So from here we can conclude that actually nuclear force is a charge independent force. It is independent of charge. It interacts with it interacts without the charge, right? It means that it can have interaction between proton and proton, neutron and neutron, and neutron and proton as well, right? So these are some of the features of nucleus force. Now the question is here that calculate the mass number of that nucleus force radius is half of germanium 72, right? That's the mass number of this germanium, right? So we know that radius is nothing. Radius is proportional to 8 to the power 1 by 3, right? Now we have to, let's suppose the radius of germanium is r, so it will be equal to let's suppose r naught 72 to the power 3, right? To the power 1 by 3. Now we have to calculate the mass number of that atom or that nucleus whose radius is half of this radius. So its radius will be r upon 2, right? R upon 2, that will be r naught times 8 to the power 1 upon 3, right? 8 to the power 1 upon 3. So if we divide them both, so it will be equal to 1 by 2, right? 1 by 2, uh, a upon 72 raised to power 1 by 3, right? So it will be equal to, the value of a will be equal to 72 upon 8, right? 72 upon 8, right? So this will be the value of a, that will be equal to 9, right? So it means that the mass number of that nucleus whose radius is half of the radius of germanium 72 will be equal to 9, right? That's the mass number. Now, talking about the Einstein's mass energy relation, right? Einstein's mass energy relation. It's a very important relation, right? It's a very important relation. So mass energy equivalence relation actually gives us the equivalent of the mass in terms of the energy, right? Equivalent of a given mass. What is the energy equivalent to a given mass in terms of the energy, right? So that was given by the Einstein, and he said that the equivalent of a given mass to the energy is given by E equal to mc square, right? E equal to mc square. It means that if m is the mass, then the energy equivalent to this mass will be mc square, right? Mc square. So that's what we call as Einstein's mass energy relation, right? Einstein's mass energy relation. We know that inside a nucleus, we have proton, we have what we call as uh, we have proton, we have neutron, right? And mass of proton is we know that mass of proton is equal to 1.0077 AMU, right? And mass of neutron is 1.00866 AMU, right? And mass of electron in terms of AMU, it's 0.000, right? 55, right? AMU. So this is the mass of electron in terms of the atomic mass units, and this is the mass of neutron in terms of atomic mass units, and the mass of proton as well, right? Now, all these masses, all the masses, proton and neutron, right? Nucleons together make the mass of nucleus, right? So what is this mass defect and nuclear binding energy, right? We know that let's suppose if we calculate the mass of proton, right? If we add these masses, we know that the mass number is the number of neutrons and number of protons. Now, if we calculate the mass of a nucleus using the mass number, right? right, we'll get some value of the mass number. But actually what happens is that when we calculate the experimentally calculate the mass of nucleus, it's actually less than that, right? Mass of an actual nucleus is always less than the masses of its constituent nucleons. And this difference between the actual mass, right, actual mass and the mass as calculated by the mass number, right, mass number, right, that's that difference we call as mass defect, right, that defect we call as mass defect. Now, talking about the binding energy of a nucleus is the energy required to split it into its nucleons, right? We know that nucleons are held together, right, with the help of nuclear forces, right? With the help of nuclear forces. So the energy that holds the energy that holds these nucleons together, we call that as binding energy, or we can say that equivalent amount of energy is required to separate all these nucleons or free all these nucleons, right, from the nucleus, right, from the nucleus. So amount of energy required to split each and every nucleon from the nucleus freely, that we call as binding energy, right? And this binding energy will be actually equivalent to the energy of the mass defect. And we know the energy of the mass defect will be, if there is delta m of mass defect, right, if delta m is the mass defect, then the energy equivalence will be equal to delta mc square, right? And it will always be positive and will be numerically equal to the mass defect, right? That will be equal to delta mc square. This much of energy we call it as we call this as binding energy, and this energy is actually which actually binds the nucleus, right? Now this binding energy can be calculated as delta m. We know, let's suppose there is z number of protons, so it will be z times mass of proton, right? Then we'll be left with number of neutrons, that will be a minus z will be the number of neutrons multiplied by the mass of neutron, right? Mass of neutron. And this will be the mass, right? This will be the mass as calculated using the number of nucleons and number of protons. But let's suppose m is the actual mass of the nucleus, right? Mn is the actual mass of the nucleus. Then this difference between the two masses, what we call as mass defect. Then the energy equivalent to this mass defect will be given as delta mc square. This energy we call as binding energy, right? This energy we call as binding energy. So this energy is nothing. This energy is what we call as binding energy. So this delta mc square will be the binding energy for this nucleus, and it will be calculated using the mass defect multiplied by the c square, right? Now let's plot the energy per unit binding energy per nucleon, right, for different nucleuses as a function of mass number, right? You can see here, if we plot a binding energy per nucleon, actually binding energy per nucleon decides the stability of a nucleus, right? It actually decides the stability of a nucleus, right? Binding energy per nucleon decides the stability of nucleus. If we plot this binding energy per nucleon, right, binding energy per nucleon as a function of mass number, you can see this is the hydrogen, deuterium, this is the tritium, right? This is the lithium, this is the neutron, nitrogen, this is the oxygen, right? So these are the elements of lower mass number, and this is the these are the elements of mass number, medium mass number, and these are the elements of higher mass number, right? So as we move from as we move right, the mass number increases, right? Mass number increases, and the binding energy per nucleon also increases. It means that these elements of lower mass number are having less binding energy per nucleon, right? It means that the elements of lower mass number, right, lower mass number or lower atomic number here are actually less stable, right? Are actually less stable. So as we move up, you can see the binding energy per nucleon is increasing continuously. So nitrogen, we can say the nucleus of nitrogen is more stable than the nucleus of lithium. Nucleus of tritium is more stable than the nucleus of deuterium. Nucleus of oxygen is more stable than the nucleus of nitrogen, and similarly nucleus of carbon is more stable than the nucleus of helium, right? But we can see it becomes maximum at the nucleus of this iron, right? Or we can say that iron has the maximum binding energy per unit per nucleon, right? Iron has the maximum binding energy per nucleon, and that maximum binding energy per nucleon of this iron is 8.8 million electron volt per nucleon. So we can say that the nucleus of an iron is the most stable nucleus, right? Iron has got the most stable nucleus, right? So iron has got the most stable nucleus, right? Now the stability then decreases, right? This is the maximum stability, atom of maximum stability, that's iron of having binding energy per nucleon equal to 8.8 million electron volts, right? It's the most stable nucleus. Then what happens is that the binding energy continuously decreases, right? Decreases. The higher and higher nuclei becomes more, they become less stable, or we can say the binding energy then decreases. And for uranium, the binding energy becomes 7.7 million electron volt, and it's very less binding energy for the uranium, or we can say uranium becomes unstable nucleus, right? That's why you, to become stable nucleus, right? To become a stable nucleus, uranium tries to split itself, right? Uh, Uranium tries to split itself, or there is a fission, what we call as nuclear fission occurs in this element, right? To this element, and so as to decrease the mass number, so that the stability or the binding energy per nucleon increases, right? So we can see that the medium sized nucleus are more stable than the light or heavy nuclei. So these light nuclei are actually less stable, and these heavy nuclei are also less stable. So intermediate, right? Medium sized nuclei are actually more stable, right? These intermediate or medium sized nuclei are actually more stable because their binding energy is great, or sufficient binding energy per nucleon, right? For them. Now, in order to, let's suppose uranium wants to get stable, uranium nucleus wants to get stable. To get the stability of uranium nucleus, right? What uranium will try to do, it will try to increase the binding energy per nucleon. So we know that the binding energy per nucleon is more in this region, right? In this region, the binding energy is per nucleon is more. So uranium will try to separate itself to get the more binding energy per nucleon, right? So it means that uranium will do a fission, right? There will be a fission process, right? And similarly, these smaller, lighter elements, right, are also less stable because of the less binding energy per nucleon, right? So to gain the binding energy per nucleon, what these nuclei will do, they will try to bind to each other so that the mass number increases, right? Mass number increases. When the mass number increases, their binding energy per nucleon increases, or we can say nuclear fusion will takes place, right? For lighter nuclei to become stable, nuclear fusion takes place so as to increase the binding energy per nucleon, and for the heavier nuclei, nuclear fission takes place so as to increase the binding energy per nucleon, right? So that's the reason we have nuclear fission and chain reaction. So nuclear friction is nothing, it's the splitting of nucleus for atomic number mass numbers greater than 230 into two or more lighter nuclei to attain the stability, right? Or we can say to increase the binding energy per nucleon, right? Uh, let's suppose uh, uh, in this, what happens in this reaction is that a certain mass actually disappears during the reactions, right? The mass is not actually conserved in this reaction. Certain mass actually disappears, and that disappeared mass actually appears as the energy, right? That disappeared mass appears actually in the form of energy equal to the delta mc square. That's the mass defect, right? Similarly, when we have uranium 235, right? Uranium 235. In order to carry out this nuclear fission, because we know that uranium will try to split itself into two fragments, because to gain the stability of the nucleus or to increase the binding energy per nucleon. So to carry out this nuclear fission, we need to initiate this nuclear fission with the help of neutron. Let's suppose this fast moving neutron strikes the uranium, right? Then uranium will split into two nuclei, barium and krypton, right? Barium and krypton, and it will also release three neutrons, right? Apart from that, it will release an energy equal to the mass defect, that's 200 million electron volt per fission, right? Per fission, right? So similarly, uranium 235 can also split into xenon and strontium, right, to become stable, and it will also release energy equal to 200 million electron volt, and two neutrons will also be emitted, right? Now these three neutrons will further strike with other uranium atoms to carry out the further fission reactions, and from those fission reactions, nine neutrons will be released, and nine new reactions will be there, right? So it will create a chain reaction, right? Because we need a neutrons to carry out the nuclear fission, right? So because of this fission, uranium splits into two or more than two nuclei, right, to become stable or increase the binding energy per nucleon, right? And the chain reaction then occurs, right? Similarly, to carry out the nuclear fusion, that's when two lighter nuclei, right, combine together to form a heavy nucleus, right? When two lighter nuclei combine together to form a heavy nucleus, right? The product is a stable nucleus, right? Let's suppose A and B are the two reactants here, and C is the product here, right? And Q will be the energy released here, right? Now, the energy released here will be equal to the mass defect, right? Once again, equal to the mass defect. And in the case of nuclear fusion, the energy released actually is less than the energy released in case of nuclear fission. So you can see here that energy released in nuclear fission is greater than the energy released in nuclear fusion per reaction, right? So it means that nuclear fission is a good source of energy as compared to the nuclear fusion, right? Nuclear fusion. So in case of nuclear fusion, why nuclear fusion takes place? Because lighter nuclei try to attain the higher stability or higher binding energy per nucleon, so they will combine together to fuse with each other, right? Uh, so that the binding energy per nucleon increase and the nucleus becomes stable, right? And there will be some amount of energy released equivalent to the mass defect of the energy, right? Mass defect of the nucleus, right? That will be equal to delta mc square, or delta m will be the mass defect. And in case of fusion, the energy released is less as compared to the nuclear fission, right? So these were the reasons that why nuclear fission and nuclear fusion actually occurs, right? Why it's because every nucleus tries to become a stable, and stability is attained when the binding energy per nucleon actually increases, right? For intermediate nucleus, the binding energy is good, so they are stable. They do not show any fusion. They do not show any fission. But as the mass number increase greater than 230, they tend to show the nuclear fission to decrease the mass number and increase the binding energy per nucleon. And similarly, lighter nuclei will be involved in the nuclear fusion to increase the mass number and to increase the binding energy per nucleon, or to increase the stability, right? So that's it for today, right? We are done with the atoms and nuclei. Now we'll be left with, we'll be starting the new chapter in the next lecture, that will be the semiconductor devices, right? So that's it for today, right? We'll meet in the next lecture. Take care and goodbye.